When you think of mathematics, what comes to mind? Perhaps it's the dusty chalkboard of a forgotten classroom. You might remember the rigid certainty of times tables or the frustrating puzzle of algebra. For centuries, this was the face of math, a tool for merchants, a language for astronomers, a discipline locked away in academic towers. It was something to be learned, and for many, something to be endured. But quietly, almost without us noticing, a revolution has been taking place. Math has stepped out of the textbook and into the very fabric of our modern world, becoming a dynamic, creative, and utterly essential force. The mathematics of today is not the same subject your grandparents learned. It has evolved. It's no longer just about finding the one correct answer to a static problem. Instead, it has become the art of asking better questions and the science of navigating uncertainty. Modern math is about building models that can simulate the spread of a virus, the flow of traffic in a bustling city. This new math is a living, breathing thing. For a long time, biology was seen as a descriptive science. It was about observing, cataloging, understanding the intricate machinery of life. We studied cells under microscopes. We traced the branches of the evolutionary tree. But a new frontier has opened up. Biology and mathematics have become inseparable partners. The secret to this partnership lies within our very own cells, the elegant spiraling code of DNA. This genetic blueprint, once a profound mystery, is now being read and understood through the powerful lens of mathematics, statistics, computer science, a field we now call bioinformatics. Imagine trying to read a library of books where all the letters have been jumbled up. This is the challenge scientists face when sequencing a genome. It's a colossal data problem. The human genome, for instance, contains over 3 billion base pairs. Mathematics provides the algorithms necessary to piece this gigantic puzzle back together. By analyzing your unique genetic code, doctors can use mathematical models to predict your risk for certain conditions. The implications are truly staggering. Artificial intelligence, or AI, seems to be everywhere these days. It recommends movies, writes poetry, and even drives cars. It can feel like a kind of magic, a ghost in the machine that has suddenly learned to think. But behind every smart assistant and every clever algorithm, there is no magic, only math. AI is built on a foundation of mathematical principles, calculus statistics. These tools let machines learn, reason, make predictions about the world. They are starting to rival, and even surpass, human intuition. At the heart of modern AI is a concept called a neural network, inspired by the structure of the human brain. Show it a picture of a cat, and the information flows through the web. Each node adjusts its own internal numbers, its weights, based on the patterns it sees. It's not thinking, it's doing math over and over, at incredible speeds. Our planet is sending us a message. Rising sea levels, more frequent extreme weather events. Shifting ecosystems are all symptoms of a rapidly changing climate. Understanding this complex global system is one of the greatest challenges humanity has ever faced. It's a problem so vast and intricate that it's impossible to grasp through simple observation alone. To make sense of it all, to predict what comes next, to find solutions, we must turn to one of our most powerful tools, mathematics. Climate science is, at its core, a mathematical science. Climate models are the cornerstones of this effort. These are not physical models you can hold in your hand, but immense systems of mathematical equations that run on some of the world's most powerful supercomputers. These equations describe the fundamental physics and chemistry of our planet, how the sun's energy warms the earth, how oceans and winds circulate heat around the globe, and how greenhouse gases trap that heat in the atmosphere. Each equation represents a piece of the puzzle, and when solved together, they create a dynamic simulation of our planet's climate. For millennia, humans have looked up at the night sky with a sense of wonder. We've traced constellations, charted the paths of planets, dreamed of traveling to the stars. That dream is slowly becoming a reality. The language we are using to write this new chapter of exploration is mathematics. From the initial launch of a rocket to the delicate navigation of a probe through the asteroid belt, every single step of space travel is a masterclass in applied mathematics. Without it, our journey to the final frontier would be impossible. Consider the simple act of getting into orbit. It's anything but simple. It requires a profound understanding of Newton's laws and universal gravitation, expressed in calculus. Engineers must calculate the precise amount of thrust needed and the exact trajectory the rocket must follow to avoid falling back to Earth or flying off into deep space. This cosmic ballet is choreographed with differential equations ensuring the spacecraft arrives exactly where it needs to be, thousands of kilometers away. We are standing on the brink of another computing revolution, one that promises to be as transformative as the invention of the transistor. This is the world of quantum computing. It's a realm that operates on the bizarre and counterintuitive rules of quantum mechanics, a branch of physics where particles can be in multiple places at once and can be mysteriously linked across vast distances. To harness this strangeness and build these powerful new machines, we need a completely new kind of mathematics. The familiar logic of classical computing is not enough for the quantum world. Classical computers store information in bits which can be either a 0 or a 1. They are like light switches that are either on or off. Quantum computers, however, use qubits. Thanks to a quantum principle called superposition, a qubit can be a 0, a qubit can be a 1 or both at the same time. Imagine trying to find your way out of a gigantic maze. A classical computer would have to try each path one by one until it finds the exit. A quantum computer, because of superposition, could in theory explore all possible paths at the same time. Our cities are growing at an unprecedented rate. They are becoming sprawling, complex organisms with millions of people moving, working, and living together. Keeping these megacities running smoothly is a monumental challenge. How do you manage traffic, deliver power efficiently, and respond to emergencies in a system with so many moving parts? The answer, increasingly, lies in data and the mathematical algorithms that can make sense of it. We are entering the age of the smart city, an urban environment where mathematics is the invisible infrastructure that keeps everything flowing. Think about your daily commute. Traffic jams are a source of frustration and a massive waste of time and fuel. In a smart city, the traffic light system is no longer on a simple timer. It's a dynamic network. Sensors embedded in the roads and cameras at intersections collect real-time data on traffic flow. This data is fed into a central system that uses mathematical optimization algorithms to adjust the timing of the lights. Money makes the world go round, and for centuries the world of finance has been a playground for mathematicians. From calculating interest to pricing complex derivatives, math has always been the language of the market. But today, two powerful mathematical forces are reshaping the financial landscape in shocking ways. The cryptographic certainty of cryptocurrencies, the unpredictable nature of chaos theory. Cryptocurrencies like Bitcoin are, at their heart, mathematical creations. Their security doesn't come from a bank vault or a government guarantee, it comes from cryptography, a branch of mathematics concerned with secure communication. Every transaction is recorded on a public ledger called the blockchain, which is secured by a network of computers all solving complex mathematical puzzles. The butterfly effect, where a tiny change can lead to massive, unpredictable consequences, is a perfect description of market behavior. And this understanding is leading to more robust strategies for managing risk in a world that can never be fully forecast. We have journeyed through the frontiers of science and technology, from the code of our DNA to the orbits of distant planets, and we've found mathematics at the heart of it all. It can be easy to look at these incredible advancements and think that this world is only for geniuses in labs or programmers at giant tech companies. But that would be missing the most important point. The future that math is building is a future for everyone, and everyone has a place within it. The skills of mathematical thinking, logic, problem solving, the ability to see patterns, are becoming fundamental skills for navigating the 21st century. You don't need to be a professional mathematician to be a part of this future, you just need to be curious. When you use a navigation app, think about the geometry problem it's solving. When you see a weather forecast, think about the immense system of equations working behind the scenes. Learning to see the world through a mathematical lens is like learning a new language. It opens up a deeper level of understanding. Your journey into the beautiful, powerful, ever-changing world of mathematics can start today.